So in this video, we're going to discuss how to set up the problem to get the ordinary least squares estimators for beta naught and beta 1. And the intuition to understand here is actually really simple. Basically, we're trying to find a b naught and a b1 that are going to help us fit a line here in the best way possible. And just to grasp the intuition as to what we're talking about, suppose that after looking a little bit at this data, I tell you that the line I'm going to fit to capture this relationship between x and y looks something like this. Now, of course that when you see this line trying to explain this data, you should be extremely skeptical, right? In the data, what we see is that higher values of x tend to be associated to higher values of y, and this line captures none of that, right? So it doesn't really look like this line does such a good job. Now, suppose that I tell you, okay, I think I understand what you mean, I think I can fit a much better line, and I do something like this. Again, now it looks like I got like at least part of it right? It looks like, higher values of x are indeed related to higher values of y in my predictions, but then again, for each person, in any case, for any value of x, I'm mispredicting, right? Like I am systematically underpredicting. Say, for example, this person with this x, I say that this person should have this much y, but in reality, anyone who has this x has a much higher y, right? So it doesn't look like this line does any like sort of good job to capture this relationship between x and y. Again, for any value of x, your prediction of how much y a person should have given that x is always too low. So can we do something to improve on that? Now, suppose I tell you, okay, now I really learned from my mistakes, now I'm going to fit a line that it looks something like this. So this is, again, a minor improvement relative to what we had before. It does look like, if you look at, say, smaller values of x, it's not like I'm missing all the time, right? Like it doesn't look terrible for low values of x. But if you start looking at higher values of x, then it doesn't look like my line is doing such a good job, right? Like take, for example, anyone who's like to the right of this dotted line. For all of these people, given their x, I'm predicting that they should have much higher y than they actually have. Now, this line should be improved. Again, for all high values of x, I am systematically over predicting. I am saying that these people should have more y than they actually have. So can I tweak this line a little bit? And I think that you guys are now grasping like the intuition as to what's going on. What sort of line would accomplish these things? And that would be a line that looks sort of like this. Now, this is the sort of line that we always see in the fitted scatter plots. But why is this line so compelling? And the whole idea here is that this line is, of course, missing sometimes, right? Like, for example, this person is right here, but I predicted for them a slightly higher y, you see? And so this is what we call the fitted residual, right? Which is this difference between the true y and our prediction for y. Now, this line is still missing, right? Like I am still having some of these residuals, right? Like I don't predict perfectly well. But the intuition behind this is that I am not systematically over predicting or under predicting, either in general or for specific groups of x's. So if you remember with the red line, I had this problem, like the line that I showed before, I had this problem where for large values of x, I was systematically over predicting. Now, this is no longer the case here. And the whole thing that we like about this line is that it kind of looks like these fitted residuals are as small as we can get. They still exist. We're never going to be able to fit perfectly, right? Given that there's variation in where these points are, But it looks like this line is not systematically making these residuals very large, So you can see that the intuition here is we want to find a line that on average will make like these residuals pretty small, right? So basically we would like to make this sum of these things, like the sum for everyone, as small as possible. And we're going to square these, because we care only about the distance, right? Like we don't care if it's positive or negative. I just want to be close to the true y. And we're going to do so by picking the beta naught and beta 1 that help us make this prediction error on average as small as possible. So to finish setting up the problem, all that we have to do is we have to replace each of these fitted residuals by their definition, right? Which, remember, it's just the true y minus the prediction that I made. So we're going to be minimizing by choosing b0 and b1. We're going to be minimizing the sum from I equals 1 to n of the true y minus the predicted value of y. And then all that we have to do is we have to replace this predicted value of y with our definition for the predicted value of y, which is just the line, right? b0 plus b1 times xi. So we're going to be choosing b0 and b1 to minimize this sum. I'm sorry, I forgot a square here. To minimize this distance between the true y and whatever I predict y should be based on x. And this is the function that we're going to have to solve. This is the problem that we're going to have to solve to find, again, the question that we have in mind here is what's the b0 and the b1 that help us, minimize this error that we're making in our predictions. So this is the problem that we have to solve, and we're going to solve it in a future video.